Well, thank you, Phil, and I'd like to thank the organizers for inviting me to talk to you. And microphone, thanks. You can just come up and yell at me, and I'll do it. And so what I want to do with my time today is tell you a little bit about 4 different projects, and I'm going to tell you very little about each one of them. But what I'm hoping is that the combination of the 4 of them and the story I have to tell you will highlight some of the really unique opportunities that electrochemistry affords for synthetic chemistry. And then with 3 of them, they're going to be marked in green, and this is not, actually I'd probably turn it on. It's pretty bad when the electrochemist can't use the battery. Okay, so, but the ones I highlighted in green are current projects ongoing, and I'm going to finish each one of those by hopefully a look towards the future with them. But I want to start today by turning the clock back 30 years and taking a look at our initial projects and what's laid the foundation for this. What I have to tell you is that 30 years ago, the community was really pretty mixed in terms of how it thought about electroorganic synthesis. And when I say pretty mixed, I mean there's some people that were really for it, and a lot of people that were really against it. Nobody really had a mixed idea. On the positive side, there was a group led by Manuel Baser, Hans Schaefer, Everett Stecken, Jim Utley, a wide variety of others, that, well, felt the way that Manuel Baser did in this quote, where he said organic electrochemical synthesis has ceased to be a laboratory curiosity, a method to be tried when all else fails, a procedure that involves mysterious black boxes and dials and wires. The science and technology are now well developed, although not mature. This was in 1986. And you could debate whether that was reality. And in fact, I had people debate whether this is reality. This is a review from my first funded NSF grant. Funded is the important word there. This proposal has 2 main elements. The first is a highly interesting investigation of reactive radical cation intermediates. The second involves the use of the unproven technique of organic electrochemistry, an effort that may well interfere with the PI's ability to accomplish the stated aims associated with the first. So electrochemistry wasn't thought of as being an aid for this. It was thought of being an impedance for it. And in fact, if you take a look at it, if that's a positive one, you can imagine what was said in the ones that weren't as positive, okay? And they were things like, well, it's unproven, requires specialized equipment, it's not general, my favorite review ever. As elegant as the science is, it won't be general, okay? So, and a method that would never be adopted by others, okay? All right, well, what we realized was that at the time, well, our opinion was that electrochemistry lacked the kind of synthetically compelling story that the 2+2 photocycloaddition reaction gave to photochemistry. So when we were doing this, everybody in our building could do a photolysis reaction, and that's because there were 2+2 cycloaddition reactions. Things like beta-lactams were made via 2+2 photocycloaddition reactions, so we all knew how to do photochemistry. But what was the electrochemical reaction, or the set of electrochemical reactions that would provide that forcing function, if you will, for the synthetic community? Well, we started out on a project looking at, well, peptide mimetics with Garland Marshall. Garland's a longtime collaborator from medical school at WashU. And the idea was to take a look at the shape of molecules that bound to active sites. And maybe we could back out differences between different active sites for particular hormones simply by looking at conformational shape. That turns out to be true, but that's another story. What we did to actually probe that was to actually take, well, the conformation that Garland Marshall would model by computer, and we would embed that conformation into a polycyclic ring system. And then we would use that polycyclic ring system to control curvature, how much it bent, actually play around with that 3-dimensional shape. But you know, in the lab, taking a look at these protons and saying, well, I'm just going to replace these with carbons, well, that works pretty well on a piece of paper. But how do you do something like that in the lab? And when you're removing carbon-hydrogen bonds and you're going to put in carbon-carbon bonds or other functionality, that means you're going to be oxidizing something. And the key was, how could we oxidize amino acid derivatives? Well, against that backdrop, we had this really nice reaction. This is the well-known Shono oxidation, first discovered actually by Ross Finkelstein and Peterson at Sprague Electric, and then really developed by a lot of people. But there was this beautiful org synth prep by Shono, and this was really how we cut our teeth on organic electrochemistry, and so many people at that particular time learned how to do electrochemistry. And it's a really nice reaction. It takes an amide, it oxidizes it to the radical cation. There's the elimination of a proton and electron. It makes an Na-medium ion, which you can then trap with methanol, then use that to trap other nucleophiles. Now, this is really an ideal tool for the problem that we were looking at, because if you actually take a look at these reactions, well, this is the one from Shono's org synprep, and it simply takes a pyrrolidine and oxidizes, it makes a T-Box protected nitrogen, and then oxidizes that in anode. And you can see that the product here is about 200 millivolts higher in oxidation potential than the starting material. This is all versus silver chloride. And that's because, well, there's an anomeric effect that ties up this lone pair with the sigma star orbital for that CO bond. And that works really well. But if you start taking a look at amino acid derivatives, well, the one we wanted for a series of substance P analogs, that oxidizes at 2.1 volts. If you take a look at a pyroglutamate, which we really wanted to oxidize, it oxidizes at 2.3 volts. There was no chemical oxidant that was going to allow us to do this. Any chemical oxidant that would oxidize this one and not over-oxidize the product would clearly not be able to hit either of these. And if we developed an oxidant for this one, well, it wouldn't do this one because of over-oxidation, and it wouldn't touch this one, and so on. So we needed a method that would adjust to the oxidation potentials that we wanted to use. Now, it turns out that electrochemistry is perfect for that, and it's perfect for that in two ways. One, you could do a controlled potential electrolysis reaction. You get a reference electrode, and you can set potentials, and that is a great way to do a chemical reaction. What we worried about at the time was we were using a standard SE electrodes, and they took agar plugs. And getting an agar plug, for those of you that are old enough without a bubble in it, is really a challenge. And the idea that we were going to get the synthetic community to start working with agar so they could try a reaction was a non-starter. But fortunately, we didn't have to worry about that, because in a constant current electrolysis, when we just put a potential drop across the cell, what happens at the electrodes is the potential climbs until it matches that of a substrate. So if you do an oxidation, that potential climbs so it matches, well, the lowest group that's going to be oxidized in solution, and then it stays there. And it stays there for most of the reaction, and if you keep the current densities low, you can push things out to 90, 95% conversion before that potential starts to climb. So in fact, you could put any amino acid derivative you wanted into the reaction, and in principle, that potential would simply adjust and allow you to do the oxidation, and that oxidation would stay selective. So we didn't have to worry about coming up with a different set of chemical reagents or a different chemical reagent for every oxidation we wanted to do. And this works really nicely. I'm not going to go through the total syntheses. This is a synthesis that we published on a substance P analog here in terms of shaping a backbone. I just want to focus on this particular reaction. It was a protecting group step. That's put the T-Box group on so that we could have the same basic chemistry that we wanted for doing the peptide coupling reactions. And then there was just this oxidation reaction, the same exact conditions of the Shono oxidation, the oxidation potential at that carbon anode adjusted to this material. We were able to methoxylate it in high yield and then carry it forward in the synthesis. So we could carry out the oxidation on this without having to develop another chemical reagent. And the same is true for that more difficult to oxidize secondary amide. In this particular case, the oxidation gives a very nice 95% yield of the methoxylated material. You can take this and treat it with a Lewis acid, put an allo group. We used this for all kinds of things. We did ozonized it and set up reductive aminations. We used it in olefin-metathesis reactions. A really nice building block. Chiral auxiliary menthol was used here because the major product fractionally crystallizes out of hexane. So it's a really nice way to get to the product. Now, a couple things hidden on here. Very clever student Larry Rutledge was working on this. You may notice that different electrolyte and a platinum wire anode, those are changes. If you take a look at the oxidation potential of this amide, it's actually slightly above the oxidation potential of methanol. And the way that Larry got to that was, number one, let's run very high current densities so that potential will start to climb. And then he used a, greasier electrolyte, something that would allow this hydrocarbon-based molecule, with this being menthol, into the double layer while excluding some of the methanol, and that's why he was able to get this current efficiency up. So using some of the unique features of electrochemistry to push this. But at its very base, what enabled this chemistry to work was that oxidation potential floating to match the substrate. And that brings us to our second story. I want to point out that that's really not just about amide oxidations. That's true for a lot of organic molecules. This is a family of reactions we've been interested in for years. In fact, was the subject of that first proposal. And we're really interested in oxidative cyclization reactions that took electron-rich olefins, things that we know of as nucleophiles, converted them into electrophiles, and then trapped them to make new carbon-carbon bonds, or we'll see carbon heteroatom bonds, make new rings and new ring systems. All the while raising the oxidation potential of the molecule. Now, the key to these reactions is this radical cation intermediate, and we don't know anything about radical cation intermediates at the time, and so we thought, well, let's do a structure-activity study relationship on these molecules. Let's take a look at how we think about radical cation reactivity. And that meant we needed to take a variety of substrates and oxidize them, and it turns out that the same problems you run in with amide oxidations, you run into with these, at much different potential levels. If you take a look at this substrate, it oxidizes at 0.6 volts. If you take a look at this substrate, it oxidizes at 1.06 volts. That's a Nernstian shift, by the way. It's the same group that's being oxidized, but this cyclization is much faster than that one. So it, well, removes the radical cation from the electrode surface, drops the potential of the reaction. Now, what's kind of neat about these two examples, if you look at this case on the bottom, you can oxidize it. You can make this carbon-nitrogen bond very well. You make a secondary amine here. That is an oxidation potential of 0.89 volts. And once again, we're back in a situation where there is no chemical oxidant that can do this chemistry. If you oxidize this particular molecule selectively, you can't ever get this one. If you oxidize this one, you can't do this one selectively. And you can't do either of these with any of the oxidants that would have been used on one of the amides. Well, once you have this ability to just change the starting material, let that potential float, you can do lots of neat things. And one of the things that we went on to do was actually probe the nature of a radical cation and start understanding things about its chemoselectivity. And I can tell you that you can put all of these particular radical cation precursors into a electrolysis reaction, just run the reaction, the potential will adjust and generate a radical cation, and allowed us to actually study series where we could actually take a look at a nonpolar case and show that it made carbon-oxygen and carbon-nitrogen bonds. We could take polar cases and push them towards carbon-carbon bond formation. That defined for us, well, what the nature of the radical cation had to be to make a particular bond. Well, initially you look at this and you say, well, this would take 6 chemical oxidants to do this, all of them operated under the same reaction conditions. That, in fact, would not be accurate because I just showed you a Nernstian shift. So the ones with carbon-oxygen bonds actually down here oxidize at lower potentials than the ones with carbon-carbon trapping groups, and vice versa over here. So actually to pull this off, since we look at carbon, oxygen, and nitrogen, would take 18 chemical oxidants that all oxidize selectively, all under the same reaction conditions. So how are we going to do a structure-activity study like this with a chemical reagent? All right, well, we've been learning that it turns out to be a little bit more complicated than that. And it's a little bit more complicated than that because, well, you have this wonderful picture of carbon-carbon bond forming reactions, and they don't all work. And they don't all work because it turns out that the cyclization reaction is very important, but it's not the only important step in this mechanism. And we've been finding more and more that this second oxidation step is an incredibly important part of an oxidative cyclization reaction. And for those of you that are thinking, well, I really love photoelectron transfer reactions. Photoelectron transfer reactions have not been able to do oxidative cyclizations to make carbon-carbon bonds. The reason they can't is the importance of that second oxidation. Now, we discovered that in part of a competition study, and I just want to highlight an important thing about this competition study. At the time we were making radical cations in the presence of a nitrogen anion, there was a potential equilibrium between those two. And really what we wanted to know was what was the mechanism of this cyclization, so we set up a competition study. This is a nitrogen radical cyclization. The alcohol wouldn't trap. If it's a radical cation, they could both trap. And what you can see from this quick diagram is that, well, you can get either oxygen trapping or nitrogen trapping, so this intermediate plays a role. But there's something else hidden here, and that is that the rate of the second oxidation is what governs the course of this reaction. If you go with a high oxidation rate, fast second oxidation step, you remove this electron, it can't go backwards, you get the kinetic trapping product. And if you slow down that second oxidation, you can actually get this to reverse and come back over this way and go to the thermodynamic product. Two important things here. One is that that second oxidation controls the reaction, and two, we can manipulate it with an electrolysis reaction because we can control the rate of that second oxidation. And that's really important moving forward. Just want to give you an example of something that we're working hard on. It's been a project that's gone on and off in my group for years because we failed every time at this. We would like to have an oxidative route to do cascade reactions, make the radical cation and pursue them. And the problem with every attempt that we've made so far is we weren't paying attention to the oxidation of that relay group. So now we're starting to probe the electronics of that group. What's the right electronics that will allow this cascade reaction? Think about how you might try to do that with a chemical oxidant. We need to oxidize to get to the radical cation, then we need to probe this second oxidation step. The electrolysis reaction adjusts for that, and we can control that by the rate of oxidation. We can actually play around with the oxidation potential at that second step. And so electrochemistry gives us an ability to probe this in a way that we couldn't do otherwise. All right, well, I told you I'm going to go through 4 stories to try to give you a feeling for things. And so I'm going to continue that with something that looks completely unrelated. But it's not really unrelated at all. But from the unrelated standpoint, we were making peptide mimetics. You want to know if they're active. And I hope nobody's a biologist in here. I apologize ahead of time. Our biological collaborators have the attention span of a gnat. Okay? They're absolutely wonderful. They say we make the molecules too slowly, and I understand that. But the point is that if you really want to get biological data on a molecule, you are going to have to start screening them yourselves. And we were taking a look at, and still are taking a look at, knocking down G protein signaling pathways with complex molecules. Some of them are 22, 23-step syntheses. So we can make them, and we now have parallel synthesis approaches to them. We can make them, but they take time. But we're also studying pathways where we're destroying biological activity and then trying to engineer selectivity for other active sites, and we don't get things that bind very well. And so we were looking for a way that would be cheap, that we could get biological data very quickly, get that data in real time. And it was with that background that we ran into this idea of employing microelectrode arrays for doing analytical measurements and probing the activity of a molecular library against a receptor. And the system is very easy, and I'm not going to go through a lot of the electrochemistry because you guys have a lot of experience with this. So I'm just simply going to tell you that what would be really nice is if you could make a molecular library and put that molecular library down onto an array such that each unique member of your library was by a unique electrode or set of addressable electrodes in that array. You can, in a classic experiment, just take that particular array, put it in with iron or another redox mediator and a remote platinum wire, oxidize it the array, reduce it the wire, and set up a, well, completely useless current at every one of these electrodes. But a useless current that you can measure, so that when you add a receptor to solution, it would bind with the molecules on the surface, would block the ion from reaching the surface below. You'd see a drop-off in that current. Well, this is a nice experiment, but there's a really big problem. And the really big problem is this is a practice array. It has 1,024 electrodes per square centimeter. But the real ones for signaling have 12,544 electrodes per square centimeter. So there's a really nice idea about taking a molecular library and building it onto an array. But the question is, how many do chemistry here and not here? And there's no way to deliver, at least using a syringe or something, a chemical reagent to that site. The only real handle you have is the electrode itself. And so the question becomes, how do I use an electrode to start building molecules at that site? And the good news is, we know what electrodes do. This is what I show all of our undergraduates when we start talking about electrochemistry. I tell them from a synthetic standpoint, what electrochemistry really does well is it reverses the polarity of things. It does Umpalong chemistry. It takes things that have a lot of electrons and it takes electrons away, or it takes things that don't have a lot of electrons and it adds electrons. So the question is, how do you use an Umpalong reaction on an array? And the answer to that question is you actually don't worry about an Umpalong on a functional group. You worry about reversing the polarity of a chemical reagent. You see, there is a way to deliver a chemical reagent to any one of those sites on the electrodes, and that's to use the electrode itself to make it. So this is an example of a Suzuki reaction. It's a palladium-0 reaction where palladium-0 does an oxidative addition to this carbon iodide bond. There's a transmetallation, and then there's a reductive elimination that forms this bond. And this kicks back out to palladium-0. Now, what we do on the array is exactly opposite of every other electrocatalytic system you see. We're not going to use the array to do a catalytic reaction. We're going to destroy that catalytic reaction. We're going to take catalytic processes and we're going to make them stoichiometric. We're going to do that so that we can, well, regenerate the catalyst at the sites where we want it. And so if you play around with the rate at which you make that catalyst and the rate at which you destroy it in solution, you can control where it goes. Well, this is an example of reduction reaction. One of my favorites is this oxidation reaction. It's done by Bicklin Nguyen in my lab on Valentine's Day. But I put it up there for 2 reasons. First of all, it is a cerium-4 reaction done site selectively on a 12K array. So the different distance between these spots are only about 25 microns. The second thing I want to tell you is that since the arrays are a series of vertical wires and horizontal wires, you can put in any pattern you want just by taking a computer program. The programs are very easy. They're just binary addressable arrays. So 1 is on, 0 is off. You turn on a vertical wire and a horizontal wire, you'll get the electrode on at the intersection. This third thing that I want to tell you about this is just hidden is pyrene. Pyrene is a really interesting fluorescent group. It fluoresces blue unless it forms an exaplex, in which case it fluoresces red. And Bicklin was using this slide not just to make red for Valentine's Day, but to show that she was getting a high concentration of the molecule down. And she's getting a high concentration of that molecule down site selectively so it isn't bleeding anywhere else. And so really nice way of doing things. Well, once you know the trick, you can do a lot of things on these arrays. And these are just, 13 of the reagents we've used. This number is about 17 now, of chemical reagents that we've used site selectively on an array. I think it's really important to remember that electrodes make acids and bases and oxidants and reductants and nucleophiles and electrophiles and transition metal catalysts and Lewis acid catalysts and Lewis bases. If you ask a member of my group what chemistry you want to move to this array, the answer is all of it. If you want to make complex molecules, you have to do modern organic synthesis in this environment, and we think that can be done. Let me show you one more example. It's one that I selected for a very particular reason. This is a copper-2 catalyzed Chan-Lamb coupling reaction. It can be done at selective sites on a microelectrode array. It couples in acetylene to a borated ester surface that we coat the array with. The reason I'm showing you this is because in our medical school in radiology, they're doing PET imaging of lots of things, and PET imaging agents always have two major components. They've got the, radioactive piece, and then they've got a targeting piece that recognizes receptors on the cells that they want to image. And those two are connected with a click reaction, which means that all of these targeting groups have an acetylene on them. And so if you want to optimize this particular interaction, you can take that molecule as it's already being synthesized at the medical school. You can stick it on an array, put that array into a solution with ferrocene carboxylic acid, and then add various amounts of the receptor. And so high amount of the receptor or a very small amount of the receptor, increasing concentration of the receptor. Looks like not a lot happens, then a whole lot happens, then not a lot happens. That should sound like a binding curve because it is a binding curve. And so if you just plot that current change versus concentration of the receptor, you can see not much happens, a whole lot happens, not much happens. You've got background surface and a negative control. This is the murine mouse VEGF receptor. This is the human one. And we use this to demonstrate that you could actually use the mouse VEGF as a model for the more expensive human protein. All right, so what do we know about the arrays before we shift gears one more time? And that is, I can tell you that we can now place or synthesize a molecule on the array, doing so complex addressable molecular surfaces. We can control the concentration of those molecules. I didn't talk to you about that, but there's a linear relationship between reaction time and the amount of stuff that goes down on the surface. We can build stable surfaces for synthesis and then convert them into tunable surfaces for signaling experiments because we can do lots of synthetic chemistry. We can use the functionalized surface to probe interactions in real time, and we also know how to use the electrodes now to recover molecules from any electrode in the array so that it can be characterized, and that gives us an unprecedented level of quality control over a molecular library that we're probing. So a really nice set of chemistry, and all of it's possible because, we're just turning around those electrosynthetic methods and using them back on an electrochemical device to increase the opportunities available to that device. These things go back and forth, and I want to tell you about one story we're really excited about. And it is this idea that, maybe we can actually take electrochemistry and think about how we're using the arrays and use that in a preparative reaction. And what we're interested in is the following idea, and that is that when you do a mediated electrolysis reaction, the vast majority of times, not every time, it happens out in the bulk solution. So a lot of times when you try to use a modified surface to influence a preparative reaction, it doesn't work very well because the reaction is not happening at the surface. But on the arrays, we're keeping molecules within 25 microns of where they're generated. So what would happen if we took the same approach to a preparative reaction? And we had, two alcohols, we wanted to oxidize one, and it was a molecular recognition event between the surface here and that molecule. That would increase the concentration of this one at the electrode surface, and by confining an oxidant just to the electrode surface, it should selectively do this one. We know we can confine tempo well. This is a 12K array with tempo confined on it. So we can confine that to an electrode surface. All right, so here's an experiment. I'm going to take two alcohols. We're going to put a polystyrene coating on the surface. Pyrene really sticks to the polystyrene coatings. And so if you have a para-nitrobenzyl alcohol and a pyrene benzyl alcohol, and you put them in a competition study and you carry out, well, just carry it to 50% conversion, you should get a 1-to-1 to 1-to-1 mix of these. And that's exactly what you get. Here is that particular study, bare platinum electrode. Tempo is the confining agent. I'm sorry, Tempo is the oxidant. This is the pyrene aldehyde product. This is the para-nitrobenzyl aldehyde product. And you can see basically a 1-to-1 ratio. If you just coat that platinum electrode with a polymer surface, you can wind up getting, well, a 1.6 to 2 ratio, no real selectivity at all because that reaction happens out in the bulk solution. But if you add a confining agent, and we just added a sugar in this particular case, if you add a confining reagent to that reaction so that you trap the tempo to the electrode surface, you can see that you can get between 14 and 17 to 1 ratio of oxidation of the pyrene alcohol. And if you can turn up the current, you can start overwhelming that, but you still get, a greater than 10 to 1 ratio of selectivity. And we're excited about this because it suggests a different way to think about selectivity in a whole series of reactions. Because there's a molecular recognition element with the surface, you can imagine that that molecular recognition element doesn't need to be next to the reacting center. It could be somewhere else in the molecule. It could be 6, 7, 10, 12 atoms away. This is how proteins work, right? You have a recognition element that can be far removed from the actual reaction site. And so can we use, well, just features of a molecule that we're looking at to induce asymmetry into a reaction, to do a kinetic resolution, to do a selective decarboxylation reaction? Everybody always asks me, what are you really thinking about? Because they know me well enough. And the answer is, if I have a whole series of amino acids and peptides that are recognized by a receptor, and I want to find the ones that really hit it, well, can I put that receptor on the surface, tie one of these to that recognize that surface to that surface, do a decarboxylative coupling with something that labels it, that allows me to pull it out of solution. And there are lots of ways to think about doing that. So we're excited about this, but if you think about it, there's something you have to have. And that is, you have to have a really versatile way of turning over chemical reagents. You have to know that when you change a mediator, that your reaction will adjust to that change in mediator. And that's what electrochemistry does really, really well. So I wanted to tell you about versatility. And so I told you about reactions that oxidize things with a range of potentials, actually from 0.6 volts to 2.3 volts with a selectivity of 100 millivolts. That would take 11 chemical oxidants that all oxidize under the exact same reaction conditions to probe that same set of systems. I told you about recycling. I showed you on the slide 13, but and counting, different chemical reagents and catalysts. And every time, you notice I didn't tell you how the array worked. It's a constant current electrolysis. It has an array, and it has an auxiliary electrode that actually just sits on top of it. It's a cap. And if I turn it on so that the array is negative, it adjusts and does a reduction. If I turn it on so that the array is positive, it adjusts and does an oxidation reaction. So same reaction that was doing all these did all of these. We can monitor binding events in real time, and we think we have at least a new way to think about doing selectivity in a preparative reaction. And we can do it because electrochemistry turns out not just to be, well, a main element of the things we do. It's the critical element. It's actually the element that enables all the others. And with that, I'd like to thank you for your attention. I'll be happy to answer any questions that you have. Oh, and I did forget, as Song said, the most important slide. My group through the years in bold, they know me and they know I get excited about things. NSF has supported our research for the last 31 years. NIH, Custom Array, and then my current group. Okay. I'll ask.
Thanks, Kevin. That was beautiful and thought-provoking. And we'll open the floor to questions.
Thank you so much. So as a materials scientist, I want to ask, most of the time the electrodes that you use are, platinum or carbon, and they're planar. And then you showed at the end that you're starting to modify them. Are there opportunities to think about more exotic materials and perhaps even nanostructured or highly porous materials to influence some of these either reaction pathways or kinetics?
Well, the answer to that question is 100% yes. And as a matter of fact, especially in this last project, we start thinking of moving towards more preparative applications. You're not going to put a polymer down on the surface and then set it up in a flow cell for a long period of time. You're going to want to have more permanent solutions to that particular issue. And so I think that there are lots of applications. Even on the arrays, the polymer coatings that we put on there, they're the ones we use. They're the ones that work. That doesn't mean they're the best ones. They're the ones that work best for us now. And you could imagine having much better control over that surface and the analytical studies that follow, if you have better control over the porosity of those surfaces and the stability of those and the never going to say the word, the sameness of them. How's that? Okay. So there are really nice opportunities for doing that. We have not probed that very much. We're at the just start of doing those kinds of things.
So, Kevin, it seems like you've outlined a paradigm which, like DNA-encoded libraries, took 20 or 30 years before Big Pharma realized and they started doing it. What do you foresee are the hurdles that need to be overcome before we see Pfizer or GSK doing this?
You're doing a microelectrode array?
Yes.
So the answer to that question is biological data they can't get any other way. Okay? So the arrays have a really neat thing, and that is this real-time signaling. And you can do real-time signaling beautifully with surface plasma resonance. There are other ways of doing it. But to do it on a library that you can then recover molecules and characterize and have the fidelity of that characterization perfect. So the same electrode that records the signal as the electrode that recovers the molecule is a technique that you don't have. So like so many different things, and so I'm a synthetic chemist, and so I apologize for that to nobody, actually. Sorry. So I apologize for not apologizing. But I'm a synthetic chemist, and to me, what lies at the heart of really taking full advantage of these things is our ability to make and manipulate those surfaces so we can ask the key question. If I'm making a complex library and I put a molecule down on an array and I study it, and then I go and I make another molecule. I want to put it down. I want to be able to study both of those molecules side by side. I can't do that unless I can recover that first one and know it's still what I put there. I have to have that. And this is what's just crippled the many of the screening types of processes that you do. Do you really know that you have in a library what you think you have? And if you're doing drug discovery, you can fish something out, and that's great. But if you're trying to map a receptor, you have to know what the conformation is. You have to know that it was configurationally stable. And that's an incredibly difficult task with something that doesn't leave you with a synthetic handle. And an electrode is a synthetic handle, and it's a really versatile synthetic handle.
Okay, well, I think we are only a little bit over time, but I think we're supposed to take Ellen should know, we're supposed to take a little break, and then we reconvene at what time? 3:30. Okay, so let's thank Kevin and Song again for great lectures.